Hello students. So today we are going to learn more about waves. In the last class we have talked about the general equation for wave, and we have seen that if we have some successive oscillations uh, in some in a string of particles, you can say, then from one particle to another particle the energy is transferred in forms of wave. That means wave is nothing but the transfer of energy uh, by some successive oscillations between some particles which are adjacent to each other. So if a wave is this one, so in that case this will be the displacement of wave. So you can, if it is a string of particles, you can easily find out where what would be the displaced position of that particle if I know where I am going to find the particle. Okay, now in that case, so here if I know that how much energy is being transferred, or uh, from initial position where I am going to find the particle, if I know that x, then easily I can find out what will be the displacement of that particle. And the equation for this is given by y is equal to a sine kx minus omega t, where k is called propagation vector. So this k is not your spring constant or some restoring constant like that oscillation. This is something different. This is called propagation vector. Okay, and this is given by 2 pi by lambda. Yesterday I told that in the last class. Okay, and this omega is nothing but your angular velocity of the wave, not for that oscillation. So you cannot use that omega is root over k by m formula here. You cannot use this because this is for oscillation. Okay, and we are talking about the omega which is now related to wave. That means the angular velocity of this wave, which is nothing but the transfer of energy, or you can say the motion of energy, one kind of like that. Sorry. Okay, now omega is 2 pi by t, where t is the time period here. Okay, so let us talk about little bit about wave intensity, and then we will come back to the speed. So what is intensity? This is a very significant term, intensity. Intensity of wave means, if I is the intensity of wave, that means it is nothing but the power divided by the area of cross section. That means what? We know that already, that wave is nothing but the flow of energy. Now intensity is nothing but the rate of flow of energy per unit time per unit area of cross section. So that is called your intensity. So if it is a source of wave, let's say it's a torch, because we know that light is nothing but a wave, electromagnetic wave. So that means the wave is being transferred like that. So if I take a small unit area here, and if I measure how much energy is being transferred through this cross-sectional area per unit time, that energy we can name as intensity. So what will be the unit of intensity? It's nothing but watt per second. Oh, already we are taking power unit, that is watt, so we don't we will not use that second inverse. We will use watt per meter square. Okay, that means power per meter square. Okay, so now on which factor intensity depends? So we can see that intensity is proportional to the amplitude square. We know that amplitude is nothing but the we know that the amplitude is nothing but the highest displacement occurred by the wave. So that means this top portion we can have the highest amplitude, the highest displacement, that is y maximum, and that we can say as an amplitude. So this is the maximum displacement of that wave. So intensity directly varies with the amplitude square. So you can say that intensity by amplitude square is always constant. So if the amplitude increases by twice, the intensity will increases by 4 times. Okay. So this is the way of expressing that how much energy is being transferred by that wave. Now we will come back to our velocity part, and this part is crucial. So if we want to find out the velocity of wave, we cannot directly do dy dt. Why? Because let's say this is the wave like this, okay, and we know that y is nothing but the displacement of each of these particles at any certain amount of time. So if I want to find out that what is the displacement of this particle, which is, let's say, x at x distance from the origin, then I can find using that formula y equal to a sine kx minus omega t at some certain amount of time. If I do dy dt, then what this would be? This would be nothing but the angular velocity, or the velocity, not angular velocity, the linear velocity of this individual particle only. So that means this particle is having an oscillation up and down, right, with respect to time, and we will get the velocity of that particle only. So dy dt will not help us here. So what we have to do? We have to look here, what do we need? Let's say this is a wave. This is a wave, and after some time what will happen? This wave will be displaced. So I'm drawing it with another color. So this wave will be displaced like this. Why? Because the wave is now flowing. The energy is being transmitted in this direction. So this is y. So this point was A right here, and this point, this A point has come this much in some certain amount of time. Okay, let's say in delta t amount of time it has gone delta x distance. So I need to know dx by dt. That means how much the wave has displaced, right? One more thing, you will see that this, if you look at this wave pattern, you can imagine an envelope here. This envelope is called waveform. Waveform. This is nothing but the envelope. So if you have some kind of wave like this, so the waveform will be like this. Okay, so waveform is nothing but the you can say a connected line with the crest and the toe. Okay, so this waveform, if you look here, so at this amount of time when point A has come delta x apart from its original point, then see the value of y is same here. So the value of y has to be same in both cases. Now we know that y is equal to a sine kx minus omega t. That means x is also changing and the time is also changing. But if y has to be fixed because a point has shifted delta x distance in some time, though the value of y is same in that case, if you look at the wavefront. Okay, so this is a single wave which has displaced delta x distance from its original point, and I want to know how rapidly this thing has happened. So I want to know delta x by delta t here. So one thing we can see that y is fixed here, right? So if y has to be same, we know that amplitude is same because this highest shift is same all the time. So a is fixed. So that means this sine part, the whole sine part has to be constant somehow, and this will be constant only if this kx minus omega t is constant, because if this part is constant, then the whole part will be constant and y will be same in both cases. Okay, so we can write that kx minus omega t is equal to some constant. So x will change, t will change, but they will change in such a manner that the total term will be constant. Now I want to know dx dt. So what I will do? I will do differentiation in both sides. We know that dx dt, if we do, k will be outside because k is a constant. We'll get dx dt. We get omega here because ddt is 1, and we get 0 here because any differentiation of constant is 0. So we can write from here that k dx dt is equal to omega. So dx dt, which is nothing but our velocity, that is equal to omega by k. And this is a very important relationship right here, that velocity is equal to omega by k. So if I know the equation of any kind of wave, and so I can find out easily the velocity. So this velocity is the velocity of the wave. So we cannot do dy dt, because if we do dy dt, we will get the velocity of that individual particle only. But I want to know the cumulative flow of energy. Okay, that is that is happening by successive oscillations of all of the particles together. Okay, so this is the thing. Now we can see here that this v is omega by k, right? And from here I can write that v is equal to omega by k, whereas omega is 2 pi by t, and k itself is 2 pi by lambda. So 2 pi gone. I can write this by t, and 1 by t is frequency, so I can write this into f. So finally I have one more very important equation, that is v equal to f lambda. So velocity of any wave is nothing but the product of the wavelength and the frequency itself. Okay, so this gives us the velocity of the wave, that means the transfer rate of the energy. Now if we talk about the practical situation, we can see one thing, that we have many formulas regarding the velocity of a wave in a string, the velocity of wave in air, and for different media. So let us talk a little bit about it. So we can talk about the string. Let's say we have a string, and somehow the string is vibrating, and the energy is flowing through the string, and you can see some wave which is moving in certain way. So in that case, what the velocity will be dependent on? We can see one thing, that the velocity of this spring, by experiment we can also see, is dependent on the tension of the spring. You can see that in a guitar, whenever you tune it, the sound changes, right? And the velocity also changes because of that. Like, because the velocity is changing, that's why the sound pitch is changing actually. So it depends on the tension. So V depends somehow on tension. I don't know the power, so I'm putting N. And V also depends on the density. So you can see mass density. That means mass per unit length. So let's say I'm taking this as mu, and this is also M, because I don't know the power. How it depends, I don't know, right? So we have to somehow find that how it depends. So we will use here dimension analysis. Okay, we will take help of dimension analysis here. So how to do? Okay, so we know that the mass density is nothing but mass per unit length. So the dimension will be ml to the power minus 1. And the dimension of tension, so tension is nothing but the force per unit length. Okay, and so what we can do here, we can easily find, and like tension is not like that, it's force per unit length, but it's force itself, right? Because tension we normally use with the force, because how to create the tension, we can directly pull a load right here, and as a result there will be tension force. So we are taking the tension only as force. So I will just write the, so this is equivalent to force. So the dimension will be ml to the power minus 2. So as we have taken this relationship like this, we can say that a V is having some dimension lt to the power minus 1, right? So now if we talk about this relation, I can just combine them. I can just write this t to the power n mu to the power m, and the next page we can do this. We can directly compare them. So V is some constant into t to the power n mu to the power m. So V is L minus 1 lt to the power minus 1, that is equal to C. Now C is a constant, so it doesn't have any dimension, so I'm not writing dimension. Then we have T, tension, that is mlt to the power minus 2, so mlt to the power minus 2 to the power n. Mu is m L minus 1 m, right? So if we just compare them, I will get some value, whereas my n will be 1 by 2 and my m will be minus 1 by 2. So if we put the values right there, so I can directly write that V is equal to some constant root over T by mu. With some experimental evidence, like you can take the data and you can see the intercept, okay, and you can see that it is passing through 1 actually. So the value of you can find out the gradient in that case. You can see that it is passing through the origin. That means there is no intercept, right? So if we just compare this with y equal to mx plus c, that means the equation of straight line. If you just take the data one by one by checking by increasing the tension, and so then what you can do, you can find out the gradient and you can show that the value of C is 1. So ultimately we will get a formula like this, that velocity is root over T by mu in string, whereas where T is the tension of the string and mu is the mass density, linear mass density, that means mass per unit length. In the same manner, if we talk about air column, some air column and the below, like some kind of wave is flowing through it, like sound wave you can say, then the velocity will be root over B by P, B by rho, where B is the bulk modulus. We have seen this modulus in elasticity chapter, and rho is the density. Now why this is bulk modulus? Now like in the same way we can do this, like using the dimension analysis. We know that the bulk modulus P is nothing but minus delta P by delta V by V, that means the stress by strain. Okay, so we know that this is strain by strain, and in the same way dimension analysis we can find this also in case of air column. Okay, now in case of a rod, you can say, like string we have said, this formula will be as the velocity will be your root over Young modulus by rho. Okay, and in the same way we can find out all of this one. Okay, now let's talk about this more about it. If we just talk about general speed of sound in so these all were about what you say transverse wave, right? Now if I talk about longitudinal wave, and if I talk about the speed of sound, then we have two different theories here. One is the Newtonian one is the Laplace one. Newton was working on it, and he said that generally we know that the equation for ideal gas is PV equal to NKT, or in a normal way you can write PV is equal to RT, where R is the universal gas constant. So we also have seen that the velocity is somehow related to the stress by the mass, that means the density, right? So in that case we can easily find out here or we have just now we have seen that for the air column our velocity is the bulk modulus by rho. So let us find out the bulk modulus, because we know that the bulk modulus is minus P by delta V by V. So I can directly find out from this equation itself. What I will do, I will just do differentiation, so I can directly write delta P V plus P delta V is equal to 0, because this side is constant. So I can write delta P by delta V is equal to minus P by V. So from here I can write that my P is minus delta P by delta V by V. So you can see here sorry, so you can see that this is nothing but my bulk modulus. So in case of ideal gas, the pressure is nothing but the bulk modulus, right? So I can easily write that the V is equal to root over B by rho. So that means this is root over P by rho. Okay, so how this has come, this equation, this has come through the dimension analysis again. Okay, yeah, there are more proofs, but for now we don't need them. Okay, so this was given by Newton, but the fact is that if we just find out the velocity of sound in the air medium, we see that it does not match with our real life scenario. That means practically it does not match, and it comes, if we just calculate this with our STP, standard temperature and pressure, we see that this is nearly 280 meter per second, which is not close to the real value. So then Laplace has come to show his way of thinking. He said that when the sound flows through air, the process is the process is so fast that the whole process can be taken as adiabatic process. Adiabatic process are those processes where the process is so fast that there is no transfer of, no dissipation of energy possible. So the energy dissipation is very, very less in that case. So in those cases, this equation will be different, and the velocity will be root over gamma p by rho, whereas gamma is a kind of constant, which is your Cp by Cv, that is the specific heat with constant pressure by specific heat with constant volume. This is not important right now for you, you can leave it, but the main fact is that Newton has told that the process is isothermal. That means it's a slow process, and we can directly do this from our equation of gas. But Laplace told no, the process is adiabatic and it happens like this. Okay, so these were all about the speed of the sound, which is required by you right now. Okay, now we were talking about, little bit earlier we were talking about intensity. Let's come to this little bit again. Okay, now if we talk about intensity, this intensity is nothing but the rate of energy flowing, okay, the rate of energy that is being transferred per unit time per unit cross sectional area. But this intensity is gradually decreased because of two different reasons. One is the spreading. What we see in case of torchlight, we see that in case of torchlight it spreads like this. So more is it goes, the intensity is decreased. So if we take this unit area, so you can see that in this A1 area the amount of energy will be more, whereas in case of this A2 area the amount of energy will be less because of the spreading, right? So spreading is a cause why the intensity is gradually decreased. One more reason is that somehow the energy is absorbed or scattered. So see, many radiation flows through some medium. So the particles in that medium can absorb that energy. As a result, the transfer of further energy is reduced, or it can scatter. That means it can reflect it in various different directions. So as a result, again spreading occurs and the intensity decrease. So these are two things which were very important in this chapter. One is the uh, energy and intensity, and the intensity is dependent on amplitude, and then the speed of light, sorry, the speed of wave. Now we have seen that the displacement, why we cannot take for taking out the velocity, because if we take dy dt, then what will happen, we will get only the velocity of that particle which is vibrating. But we need to know that how the energy is transferred. So if we take the waveform, and then if we see how much it is shifting with respect to time, that is, if I take dx dt only, then I can get the velocity. And we have seen that the velocity is omega by k, whereas k is nothing but the propagation vector. And we have also seen that v is also equal to lambda f, that means wavelength into frequency, which is very important formula. And we have seen that in case of string, the velocity can depends like this, that is root over t by mu. Okay, so if I don't know the lambda and frequency like that, only if I know a string and if I know the mass density and the tension on it, then I can easily find out the velocity. So like that, we have the same velocity in case of air column, and we have seen that if I find out the bulk modulus in that case, from this formula I can easily write that the velocity of sound or wave through that air column is b by rho, which is your nothing but p by rho. Ultimately, rho is the density. Okay, but this was given by Newton and it is not accurate. So Laplace has told, no, when the energy is flowing, when the wave is flowing, the process is so fast that there is no way of dissipation of energy. So it is an adiabatic process, and that's why that gamma has come here, which is nothing but the ratio of the specific hits. Okay, so that was basically today's study, and we know that the further studies will be your Doppler effects and the superimposition of waves. So for today, this much is it. Bye bye.